All right, good morning to everyone in Microsoft Teams. Okay, I have 11 o'clock and I definitely want to go ahead and get started a little bit on time today. All right, I have the recording started, so if you have any questions or comments or anything private that you would like to discuss with me, if you can wait until I end the recording and then we can discuss those things after class. All right. So I did promise you guys a review. All right. I wanted to review chair confirmations and talk a little bit about acyclic confirmations, do Newman projections, and do a naming exercise. But I'm not prepared to do that today. All right. So what that means that I'm going to have to work on that and get it to you outside of class. So be on the lookout for some questions. I might have a Word document or I might have some PowerPoint slides that I sent to you guys where I have that information built in. We'll try to talk about that content on Monday. All right. You guys should have got some practice quizzes from me. All right. So that means that you guys know that I've been trying to build my quizzes in Canvas right now. So you might get that this weekend. If not, it'll be next week. All right. So keep in mind that there will be a quiz concerning naming and a quiz on confirmations that will be in Canvas before your test. Also keep in mind that Friday coming, that should be October the 9th, you're going to have test 2. That's going to cover chapters 3 and 5. All right, that test will be after class. All right, so that means that I will have Friday's class. I won't be teaching anything new, but we'll be just reviewing the material that we've been trying to learn up to that point. And then most likely, I believe probably right at 12, if you need to come in person, you can take that exam. Also, if you want to take it on Respondus, you can. All right, that program is working better than it was a few weeks ago. So I'll be able to have that exam ready to go by Friday in Respondus. Keep this in mind if you want to do your exam electronically. You must have access to a webcam and you must have access to the lockdown browser. All right. If you don't, you're not going to be able to take that exam. All right, there is a practice exam that I will make available to all you guys. Just one question. If you want to test your setup, you're more welcome to do that. All right, we'll talk more about all this stuff on Monday, but I think you guys should know that definitely your test is coming up on Friday. It's covering chapters 3 and 5, and that I will be sending some more content to kind of review things that we cover in chapter 3. All right, today I just want to introduce chapter 5 and some concepts. We'll work this out more Monday and Wednesday, and I'm hoping that on Friday's class that it'll just be a review, and most of you guys will be ready for your test right after that on Friday. Okay, so let's
Got
move. You got a
that
question?
can't
Say that one more time.
get some people that can't get in.
Okay, who can't get in?
Kayla Jones, Asia Fitzgerald, Zaria Moore. Um, yeah.
It's almost like the same people every time. But Kayla Jones, who else?
Zaria Moore.
More. Okay.
Asia Fitzgerald. Alicia Moore.
All those students you just mentioned. Okay, let's move into chapter 5. Okay? It's a very important concept that comes up in chapter 5, right? And that's stereochemistry. All right. And if you want to think about stereochemistry, the way that we like to think about this, and this is the atom that has, or we think about two separate carbons that have the same connectivity. They say we have 4 things attached to a carbon. So they're all 4 separate things. All right. Within these 2 molecules, there are different ways that they can orient in 3-dimensional space. Right. So let's say this carbon has an oxygen, a bromine, and an iodine, and an H. And in one structure, I have the oxygen pointing towards you. I have another carbon that has those same atoms, but in this case, the oxygen is pointing in the back.
I
Right?
just you're looking
Are you
at.
showing something different? We just see the main screen.
Yeah, I'm not showing anything. I'm just talking.
And says
All right, you have to use your imagination here. Sorry, I know. Maybe I should have prefaced this. All right, to get a handle on stereochemistry, you want to have to start to use your imagination. You want to start to visualize things if you can. And I'll try to jump. Maybe I'll do this. This could be a help. Let me see if I can use my program here, my visualization program. It's not going to work. Sorry, I shouldn't be so negative. It's just that my computer seems to always move slow when I got all this stuff going on. Okay, it might not, I just asked for it to download, but it's taking forever. So if you guys don't mind, just do right now, you have to do an imaginative discussion. Just kind of try to imagine what I'm saying. I have one carbon that has 4 atoms attached. There's an oxygen, a bromine, an iodine, and an H. In this structure, oxygen is on a wedge, meaning that it's pointing towards you. I have another carbon that has the same 4 atoms, but this oxygen is pointing in the back, all right? So both of those carbons have the same atoms connected, and the only thing that's different is its 3-dimensional space, right? One atom has an oxygen and pointing towards me, and another carbon atom has those same 4 atoms now where the oxygen is pointing behind me, all right? That's a basic way to describe stereochemistry, all right? If I didn't know that how things are oriented in 3-dimensional space matter, you would tell me that those 2 molecules are the same, right? There's a carbon that has all 4 of the same atoms. But in this chapter, we're going to learn that the way that things are oriented in 3-dimensional space matters, all right? And that discussion is called stereochemistry. So again, stereochemistry is looking at how similar carbons or carbons that have similar atoms attached, how they differ the way that they oriented those atoms in space. That becomes very important. Okay, so the first thing that comes up when we need to study this type of stuff is this word that comes, or a word that comes up that is chiral. All right, and chiral is a word that tries to explain a unique phenomenon when I look at my hand and imagine the mirror image of my hand. So take a look at this slide here. I have my right hand. I'm not too sure if you're home or if you have a mirror next to you, but if you can do this experiment next time that you look in the mirror, all right? If you place your right hand in the mirror and you look at the reflection of your right hand, you see what? Your left hand, right? Okay, so your right hand it reflects to your left hand, right? No different if you have letters on the shirt and you look at the reflection, right? It looks like it's running in the opposite direction. Sometimes you can't read the letters in the reflection, right? So reflection does not give me back the same image. And there's a word that we like to use in chemistry to describe that phenomenon. We like to use the word chiral. If you look at the definition down here, the mirror image is different from the original object. That means when I look at the reflection, it's not the same thing, all right? And chiral, this kind of come from the word hand, it just means handedness. And the first, when people examine this phenomenon, they thought of their hands, right? So we use the word chiral to come back. The hand has that property. When I look at the reflection of my hand, it's not the same thing. However, if I gave you a round ball and I have you to look at the reflection, is it different or the same?
It's the same.
It's the same, that's right. So not all objects have that chiral property. And that makes this chapter something that we have to think about, all right? That's why the word chiral comes up. Only chiral objects will give different reflections. And that's not every object in the world. Again, we just described, my hand gives a different image, but if I gave you a circular ball, it will give the same image, okay? So the word that we like to say when that image comes back the same is achiral. All right, so when I look at my reflection and it is exactly the same, that molecule has no handiness, or it has no properties that make it look different when I look at the reflection, so we call that achiral. Okay, so is everybody cool with the word chiral, achiral? All right, chiral means handiness, and what's unique about my hand is that the reflection will look different, right? And achiral molecules are molecules that don't have handiness, or the reflections are not different when I look at them. Okay, great. Yep.
I can't see
Good.
your screen share.
Okay, you can't see my screen. I'll stop and share one more time. I'll stop the sharing, and then I'll reshare. Okay? Show of hands. Can you hear and see my screen? If you can, will you mind raising your hand? Okay, good. Good, good, good. We got a few hands. All right. Just to review really quickly, one more time. We're trying to make sense of this word. I'm going to be using this word all over the place. So I want to make sure everybody's comfortable with it. The word is chiral. All right? Chiral or chirality. This means handiness. All right? And handiness means some property of a hand. Right? And you guys know that a hand has a thumb, 4 fingers, right? Blah, blah, blah. It's a hand. That's what chiral means at the basic level. It's just hand. My hand has a unique property though. Whenever I examine the reflection of my hand, I get back a different image. In this case, my right hand will reflect to look like my left hand, right? Okay? So I don't get the same image back when I reflect it. So that's a unique property of hands. We like to call that chirality as well, right? Being chiral is that my mirror image, is different. However, achiral molecules give back this same reflection. So if I put a circular ball in a mirror, it looks just like that ball, all right? Those are achiral molecules. So our first big word here for us this chapter is the word enantiomers, and we're going to break down the word stereoisomers as well, all right? A stereoisomers, and we've been working on the word isomers in this course. We talked about constitutional isomers. We also talked about geometric isomers. Now we're dealing with stereoisomers, all right? So stereoisomers are atoms that have all the same connectivity but differ in 3-dimensional space. I'll say that one more time. A stereoisomer has all the same atom connectivity, but they differ in 3-dimensional space. I'll say it one more time because I'm hoping it'll stick this time. A stereoisomer has all the same atom connectivity, but they differ in 3-dimensional space, right? You guys remember when we talked about isomers, there has to be something that differs, right? Constitutional isomer differs by the way they connect. Geometric isomers differ by the way they're oriented around double bonds or in rings. And stereoisomers differ by the way they are oriented in 3-dimensional space. Okay? So our first term within stereoisomers is this term called the enantiomer. All right? These are compounds that are non-superimposable mirror images of one another. All right, so let's take a look at this. And that means that they are 2 completely different molecules, right? So if I look at this carbon here, and I'm hoping everyone can see I'm going to a laser pointer here. See the laser pointer here, right? This carbon right here, and typically we like to give these carbons a star. We'll come back and talk about that shortly. All right, this carbon has a hydrogen, a bromine that's brown, an alpha group, and a methyl group. Can everyone see that? That this central carbon has an H, a methyl, an alpha, and a bromine. All right. If I look at the mirror image, I get another molecule here that has the same thing attached. A bromine, an H, a methyl, and an alpha group. All right? And this is where you guys are going to have to use a little bit of imagination. If I can get my drawing program up, I will try to show this to you. All right? I used to teach this with a model kit. But if I pick this molecule up right here and try to place it where I match all the atoms back up, all right, you have to take my word for it until I can show you that these atoms will not match back completely. All right, there'll be an issue. Typically, if you try to overlay the methyl and the H and the bromine, the alpha group will be on this one on the left side and the alpha group will be on the right side. There's no way that I can properly lay these on top of each other. All right, even if I try to flip this over to where the alpha carbons are laying on top of each other, this is going to mess up to where the bromine and the H, they won't be in the right positions. All right, so non-superimposable. To superimpose means I can place one object on top of the other. If you are in your home or in the room, classroom with me currently, your two hands are superimposable, right? So if I took my left hand and I tried to superimpose it on my right hand, do they match up completely?
No.
Kind of, but they're not perfect. They do a good job, right? So my left hand, because my thumb is pointing towards my right hand side, right? I got my palm down for my left hand, and I got my right hand, I have to make it palm up, right? To try to superimpose it, right? So they kind of match up. My thumbs and my index fingers and my pinkies, everything is somewhat matching up, but there's a big difference. What's the difference there? Is that for my left hand, I have to have my palm down, but for my right hand, I have to have my palm what? Up, right? So that means I didn't get a perfect superimpose. Superimpose means that everything has to match perfectly, all right? So I have to have both hands palm down to see if they're a match. And if I did that, I realized that my left hand and my right hand are non-superimposable. So my right hand and my left hand are what to each other? That they were chemical compounds.
They're isomers.
Isomers. What type of isomers?
Enantiomer,
Yeah,
whatever it's called.
that's right. They're a stereoisomer, and to be more specific, you would say they are enantiomers because they are non-superimposable mirror images of each other. That's very important. Not
Yes,
only.
and Adora can't get in, Dr. Cooper.
Okay, I see her name. She's in the lobby. All right, she should be able to get in. Okay, these should be non-superimposable mirror images. So not only are you my mirror image, but you're non-superimposable. If I looked at that ball in the mirror, right, and I took the ball that's in my hand and the reflection of the ball that's in the mirror, can I superimpose the ball on top of each other? Will they match?
Yes.
Yeah, they'll match. They will. They will. The two balls, because they're circular, right? So because they're spherical, they're going to be easy to fall into place. There's nothing missing in two spheres. They'll fall in perfectly. But my right hand and my left hand, they can't fall in both palm down, right? So that's what makes those enantiomers. All right, good. So the basic definition of enantiomer, again, are compounds that are non-superimposable mirror images, all right? For an organic molecule to be enantiomer, it must have a chiral compound, all right? Or it might have a chiral carbon. We're going to talk about that. All right. So any molecule that's chiral will automatically have an enantiomer. That means that any molecule that gives a reflection of a different compound, or if its reflection is not the same, it will have an enantiomer. And that reflection is typically the enantiomer. So I took this molecule and I examined the reflection, and this molecule here is the enantiomer. All right, before I move forward, this came to my mind, and typically in the past, when I can look at students, I kind of got that vibe and I can modify my teaching. So it's kind of weird right now to teach to you guys that I just
Dr.
see.
Cooper, I'm not meaning to interrupt
Go ahead.
you or anything, but I can't see anything. Like, do you have anything on the screen?
Yep, I have a whole thing showing.
I see nothing.
I'll try one more time to shop. I'll stop the sharing and I'll reshare. Okay, I'll take one more set of hands. If you can see and hear, would you mind raising your hands? If you cannot see but you can't hear, would you mind letting me know? Okay, thank you, Ms. Faye, for trying. Got you in. Okay, good. I saw hands, so I'm assuming that everyone can see my screen. All right. So again, enantiomers are non-superimposable mirror images, and any molecule that we deem chiral will have an enantiomer. All right, that's how it works. I'm going to have a reflection that's not going to be the same, and that reflection is going to be my enantiomer. All right. So before I move forward, I wanted to say this. Why is this phenomenon even important in organic chemistry? Why do we have to learn stereoisomers, and why do we need to learn enantiomers? All right. The reason is because it came from biomedical research. There was a drug that was on the market that was called cisplatin, right? And chemists made this complex in different various ways. And because of the way that they were preparing it, they got different ratios of orientations in space, right? So one guy was making maybe this enantiomer, another person was making a different enantiomer, right? And so they didn't care from the chemistry perspective, those molecules were the same because they had all the atoms arranged or attached to the same atoms. So they said, this is this drug because I have all the atoms attached correctly. I got the same atoms attached correctly here. So they were giving patients different variations of the way that they prepared the drug, right? And they realized that some of the patients were being healed of cancer and others were dying. And they could not understand what was wrong, right? All of the data was saying before we gave you the drug, we knew that we had all the atoms attached correctly. But there's one thing that they did not care to, or there's one thing that they really did not take into account at that time. And this is before we had very advanced instruments. What do you think they didn't take into account? The way that the atoms were arranged in three-dimensional space, right? They knew that they had all the atoms attached to the correct groups or other atoms, but it did not take into account the way they were attached in three-dimensional space, right? And so when they went back and studied that, they realized that certain people that were being cured had the right enantiomer given, and those that did not, or those that were dying from the drug, had the wrong enantiomer, all right? Now the FDA says, any drug that comes to market, you have to tell me which stereoisomer you're dealing with, all right? Unless both stereoisomers are productive, all right? And that becomes very important for us as society, right? We are taking organic chemistry to move into something else. Maybe I want to be a nurse. Maybe I want to be a doctor, a veterinarian, a dentist, a pharmacist, etc., right? I need to give people some type of medication, some type of small organic drug, organic molecule drug, right? And it's going to be very important that I understand the stereochemistry of that molecule, right? Because one enantiomer can cure you from this, and another enantiomer can actually cause some issues, all right? The body is very sensitive to chiral molecules, all right? So this is why this topic becomes very important, because as a government and as you guys are going to be growing to professionals, the stereoisomer of that molecule that you would have to admit to someone becomes very important, all right? So keep that in the back of your mind. So let's talk about this chiral carbon. There's some other descriptive terms that we like to say about it. We call it an asymmetric carbon. And this is probably the easiest way to think about finding a chiral carbon, is that it's a carbon that has 4 different groups. That's the easiest way to determine if a carbon is chiral. I don't have to get a mirror and look at the reflection. I just look at how many groups are attached to that carbon. If there's 4 different groups attached to the carbon, it's automatically going to be called a what? A chiral carbon, the same thing as saying an asymmetric carbon. Any questions from anyone? All right.
I have a question.
You got a question? Yes, ma'am.
So you said it has 4 different groups connected
That's
to
right.
it.
That's
Does
right.
it matter like which groups or any?
Any 4, as long as the groups are different, it's fine.
Okay.
Okay, let's go back. Let's look at this example that was on the board. For the carbon that has a star, this carbon right here, what are the 4 different groups? We just established that that molecule was chiral, and it had a mirror image that was an enantiomer to it, what are the 4 different groups to that carbon? What will you tell me?
We just name them like methyl.
Ethyl, methyl. Are you talking about those type of groups?
Yeah, that's a group. That's right.
Okay, yeah. Ethyl, methyl.
Bromine and hydrogen.
Yeah, this carbon has 4 different groups, right? There's an alpha group here, right? 2 carbon constituent. There's a methyl group here, which is a 1 carbon constituent. There's a hydrogen that's in the back, right? And there's a bromine attached. So that this carbon is a asymmetric carbon, but also known as a chiral carbon. And we know because I have a chiral carbon, that molecule will have an enantiomer. What if I look at the methyl group? Is that carbon chiral?
No, it's achiral.
Okay, good. If I look at the carbon of the methyl group, it only has 2 different groups, right? It has 3 hydrogens, they're all the same, so that's 3 of the same group, and then it has this big chain down here, which is this like propyl-bromone group, right? Right? So this carbon of the methyl group does not have 4 different things. It has 3 of the same, which is 3 hydrogens, okay? So that carbon is not chiral. Good, you can say it's achiral. All right, so I can identify a chiral carbon by just looking at the number of different groups, and they have to be all different. All 4 groups have to be different. If I have that case, that carbon will be chiral and will have an enantiomer. Okay? Any questions so far with a chiral carbon?
Can you go back to the last slide really quick?
Can I go back to the last slide? Yep.
Thank you.
Don't forget, these slides are provided for you guys, so you can. They should already be in Canvas. Okay, let's move forward. Another term that comes up is a stereocenter. All right, very important that we kind of keep these terms in mind. I used to give a definition type of question on this chapter's exam, so I might go back to that to make sure students are keeping track of these words and what they mean. All right, the best way to think of a stereocenter is this. It's any center where when I exchange groups, I generate a new enantiomer or a new stereoisomer. That's the fundamental definition, sorry. So if I exchange any atoms around a center and that generates a new stereoisomer, that carbon or that center or that atom is known as a stereocenter, okay? So right here, this is a nice definition. If you can see my laser pointer, a stereocenter or a stereogenic center or atom is any atom of which the interchange of 2 groups give a stereoisomer, right? It's the same definition I'm trying to give. If I look at an atom and I move things around, you can move only 2, that still works, and I generate a stereoisomer, that center or that atom is classified as a stereocenter. All right? For carbons, and this is kind of convenient for us, if the carbon is asymmetric, it's a chirality center, and that chirality center is also a stereocenter. All right? So for carbon, it's pretty easy. If a carbon is chiral, it's asymmetric. And if a carbon is asymmetric, it's a stereocenter. So those words are synonymous when I'm talking about the carbon atom. For a carbon atom to be chiral, it had to be asymmetric. And for it to be asymmetric, it's a stereocenter. All right? There's other things, though, outside of carbon, right? There could be nitrogen, oxygen, etc. So that's why some of these terms are different depending on the atom. We'll do an example here shortly. Asymmetric carbons and the double bonded carbon atoms in cis-trans isomers are also stereoisomers, and these are the most common types of stereocenters. I'm sorry. We'll do an example of that shortly, all right? So asymmetric carbons are stereocenters, and carbons involved in cis trans are also stereocenters. We'll make a distinction between the two, all right, in the next example. Let's take a look at this. So this molecule right here, we just talked about this earlier. This is the carbon that had an alpha group, a methyl group, a bromine, and an H. That carbon right there is chiral, so we give it that star. And that carbon is a stereocenter. We give it the pink circle. I think everybody's comfortable with that. If a carbon is chiral, it has to be a stereocenter. And it's also an asymmetric carbon. Let's look at this nitrogen. It also has a star and a circle. It's chiral. Why? 4 different groups, right? I got a methyl group. What is this group right here called?
Propane.
A propyl. We'll use the word propyl because we were just trying to say alkyl group. So that's a propyl. What about this group right here?
Ethyl.
That's an alpha group. And right here, what is that group, this group right here called?
Propyl.
Not propyl. This is branch, so this is an isopropyl right here.
Oh,
So-
if it has a subscript, it's branched.
I'm not too sure. These have subscripts too.
No, I mean like if it has a parenthesis and it's like two representing 2 compounds.
That's too general to say that. There's a lot of, I can draw a molecule that has atoms and parentheses that are straight chain. You want to transpose this in your brain to a line angle structure, right? This is the carbon with 1 H that has a methyl, that has 2 methyl groups. So that comes up branch in this case. But just because I wrote something in parentheses doesn't mean that it's branch, right? Just for this case, this is how that sustention looks, is branch. I hope that answered your question. The best bet is just to redraw this as a line angle structure, right? And you should be able to see that this is branch. So this nitrogen has 4 different groups, right? Propyl, ethyl, isopropyl, and methyl, right? They're all different. So this nitrogen is asymmetric and it will be chiral. And then it's a stereocenter because if I move any 2 things here, I will get a stereoisomer. These 2 carbons of this double bond are stereocenters. Let's think about that first. Why? Why would they be stereocenters? So let's say that I move this methyl group over here and I put the H over here. Would that change this molecule?
We can't see where you pointing.
Should be to the laser pointer right here. If I had this methyl group and I moved it from here to there and the H over here, would that change things? Okay. Someone in the class said yes. And hopefully you guys can see, as drawn, I got 2 methyl groups on the right-hand side of this molecule, right? This orientation is called cis, right? 2 of my largest extensions on the right-hand side. This is a cis orientation. But if I exchange just the 2 atoms on 1 carbon, if I put an H on the right and the methyl group on the left, now this molecule will be called what?
Trans.
That's right. So that means that this carbon is a stereocenter because when I exchange things, I get a different isomer. And the same thing here. When I exchange things, I get a different isomer. All right? But they don't have that star. Why don't they have the star?
Because you're like
It's not a
chiral.
center.
Good. They're not chiral though, right? And how do I know that? They don't have 4 different what?
Bonds.
All right. They don't have 4 different groups here, right? That's the easiest way to tell if a carbon is chiral. Just look at the number of groups. Instead, this carbon only has an H, a methyl, and this methylene double bonded carbon down here, right? This carbon only had a total of 3 groups anyway, right? So it couldn't be chiral because I need a total of 4. So this carbon and that carbon are not chiral carbons. Instead, they are stereocenters. Because these 2 carbons are not chiral, I cannot draw a what for this molecule?
Star.
Or, okay, good. I can't draw the mirror image, or in other words, I'm really trying to say I don't have an enantiomer here. All right? So these two carbons don't have an enantiomer. And we'll talk about what happens in this case. It's something else. But I don't have a mirror image that's not going to be my reflection. Okay, good. Let's keep moving forward. Achiral compounds, right? We just established that this is a molecule that don't have a chiral center. All right? They do not have enantiomers, and the reason is right here on the board. If I took my mirror image right here, if I took my compound and looked at the mirror image of it, which would be this compound here, this compound, you can just rotate it and it'll look exactly like my first compound, right? These two compounds are superimposable, right? I can directly place this molecule on top of that one, right? Everything would match perfectly. So because my mirror image is superimposable, I cannot be an enantiomer, all right? And that means that this is just the same compound, all right? So this is just an achiral compound. In other words, I can't generate any stereoisomers here, all right? When I try to, I get back the same compound. So I don't have any stereoisomers for this type of carbon.
Dr. Cooper, but couldn't you change the other ones around 180 degrees and they become achiral?
Where? Which one? You mean for the chiral center?
On the previous slide.
Want me to go back? Which slide? To this one? Or
It was the other one. Yes, no, go forward one. Yes, like couldn't you? No, yes, this one. No, you couldn't do because they're the same. Oh, because the two threes were the same.
Yep. In this case,
That's why.
yep. If you try to rotate this one, you can rotate the one on top and the two on top. Let's do that. It said we rotate the one and the two on top. The issue will be between 3 and 4 if you did that, right? You will have a 4 up front and you have the 3 in the back if you try to rotate this one on top of it.
So
Alright.
are you saying like that this doesn't work because there's not 4 different groups?
If you can summarize it that way, that's the simplest way to think about it. But I'm just trying to give you guys a pictorial explanation. The mirror image is non-superimposable. That means there's no way I can stack all atoms directly on top of each other, which is a consequence of having 4 different atoms, right? So I was just trying to say earlier, you don't have to do this mental exercise if you know that the carbon has 4 different groups. Someone has done that work for us, and we just take their studies. The study came out that any carbon that has 4 different groups will automatically be chiral. All right? But if you want to, you can use this as a way to explain that. If you took the mirror image and you try to stack it back, which is the same word of trying to make it sure if it's superimposable, it won't impose correctly. You will have some mismatches, right? You might get 1 and 2 to stack, but 3 and 4 will not stack correctly. However, if I have a carbon that's achiral, that means that I don't have 4 different groups on it. And if I try to now stack its mirror image back, it does stack, right? Perfectly. That means this compound is superimposable, and this is not an stereoisomer. Again, we said that my reflection has to be different, not the same. What happened here was that my reflection ended up being what? The same. Just like we said a ball was, right? That means a ball is achiral. If I took the ball and look at its reflection, it's exactly the same. That's not my stereoisomer. We're oriented in space the same, right? Chiral carbons have the ability to orient things in 3-dimensional space differently. And because my reflection is oriented differently than I am, we are stereoisomers to one another, which becomes very important in drugs, right? We talked about that. If you give me the wrong stereoisomer, I can die, right? There's compounds that have one stereocenter different, and they have two different smells. That's how sensitive the body is to chiral compounds. That's why, as growing organic students, we want to be careful there. All right, did I answer any questions there? Is everybody getting comfortable with that explanation? If anything, I just want to make sure this is easy to think about like this. Any carbon with 4 different groups will be chiral. It's going to be a stereocenter. It will generate enantiomers. Okay? Which is a stereoisomer. And that's what we're trying to pick up in this chapter. Any other carbon that doesn't have 4 different groups will not generate stereoisomers. All right? I can easily determine or easily look at a molecule and determine if it's achiral by looking at a plane of symmetry. So if I look at this atom here, or yeah, this molecule here, right? The plane of symmetry is right down, I guess the center here. Where on the left and on the right, I got this same atom, which is 3. So molecules that have plane and symmetry are typically not going to be chiral, right? So that's another trick that we can look for achiral. If I see symmetry, there's not going to be chiral, right? So if I look at this cis, if I look at these 2 atoms in this fiber ring that are cis to each other, right? There's a nice plane of symmetry right down the middle. I look at the right and I look at the left. Both of those chlorines are on the bottom face of that ring, all right? And so they have the same look, or they kind of reflect each other from left and right. So that symmetry makes this whole molecule what? Achiral, right? This molecule becomes achiral. We'll talk about a specific term here that's called meso. Meso really means I have stereocenters, but my whole molecule is not chiral. So it's possible to have stereocenters, but overall I become achiral. And that happens here. This carbon and that carbon are stereocenters, but overall the molecule is achiral. If I look at trans, again, same thing. This carbon and that carbon are stereocenters again, right? But now I don't have a plane of symmetry, right? Those chlorines don't match up correctly when I try to divide this molecule in half. So my reflection becomes my enantiomer. So that means that this molecule is now chiral. I can generate a stereoisomer. Okay? Any questions with that so far? Plane of symmetry is going to kill chirality. You're not going to be chiral anymore. That's another trick to help us determine if a molecule overall will be chiral or not. All right, and this will be the last thing. I'll talk a little bit about this and we'll come back to it on Monday, is the R and S configuration. All right, so that's going to help us determine what you are talking about. Or another way is that if I ask you to draw an enantiomer, I can give you some information out. I'll tell you that the chiral center is in the S configuration, or I'll tell you that it's in the R configuration. And that information will allow you to draw back the correct molecule. All right, so we're going to be using R and S to describe the configuration. And keep this in mind, a conformation is just how you are oriented, right? Am I around double bonds or around single bonds or around rings, right? Rotation. A configuration is telling me how you look in 3-dimensional space. And what should be very important here is this wedge and dash that you start to see on carbons now, right? So in one structure, we're going to have a wedge and dash. Another structure, we also have the wedge and dash, but things are mentioned differently, right? And what you guys are going to learn here, and hopefully we can get to this before the end of today, one enantiomer is natural, right? Aniline is going to be one of your amino acids, all right? This is the natural configuration, and this is the unnatural, right? I mean, that means the body probably can't really digest it at all. So if you're taking the wrong enantiomer, it just kind of gets weeded out of the body, all right? So this compound that's natural is biologically active, all right? And we need a convenient way of describing how to draw these, and we use RNS to talk about the stereocenter. All right, so what comes up is the call, Ingol, and preload convention, all right? We'll talk about this. You want to set priorities for your 4 atoms, all right? We've been talking about priorities already, but you want to start priorities, all right? The higher the atomic number, the higher the priority, all right? If I look at priorities and I see the rotation of those groups are clockwise, we call it an R configuration. And if I look at priorities and I look at the orientation of how things are rotated and it's counterclockwise, that would be an S configuration. And I can't draw all that today, so you guys just have to listen to me. All right, but these rules are what we're gonna use to determine if something is R and S. Again, it's like 3 simple rules. I set priorities for all groups, and I look at the rotation. If the rotation between 1 and 3 is clockwise, that's an R configuration. And if the rotation of those priority groups are counterclockwise, we say S. There's one big important thing that we have to keep in mind, is that we have to always orient the molecule with the H's in the back. Okay, that's very important. So when I'm looking at the rotation, the H has to be in the back. And there's some tricks that if the H isn't in the back, we can do. So we learned that priorities are based off atomic number. If I look at these atoms, I has an atomic number of 53. Bromine has an atomic number of 35. Chlorine has an atomic number of 17. Sulfur has an atomic number of 16. And oxygen has an atomic number of 8. Okay? So you guys have to realize, I'm sorry, fluorine is 9. So the higher the atomic number, the higher the priority. And higher priorities would be given the number 1. Okay? The second priority will be 2. The next lowest will be 3. And the lowest priority is 4. The way to think about priorities is like the number 1 thing in your list you got to get done. All right, so the highest priority has to be the number 1 thing that you need to do. There has to be 1. Highest atomic number needs to be 1. All right, so atomic number is going to give you priorities. So look at the example really quickly. If I had to look at my 4 groups, I got fluorine, a methyl group, an H, and an NH2, right? And all you need to do to assign priorities first is just look at the first atom attached to the chiral center. Fluorine is attached first, nitrogen is attached first, hydrogen is attached first, and carbon is attached next, or attached first, I should say, right? So if those groups are different, it makes my life easy, and I can go ahead and just work with the first atom attached. If not, we'll learn in the next slide what to do with those cases where there's some matches. There might be 2 carbon groups. I have to work those out. So if I look at fluorine, nitrogen, H, and carbon, and I had to determine my priorities, I know that fluorine has the highest atomic number, then nitrogen, then carbon, then H, all right? You want to go ahead and keep this in mind. H is always going to be the lowest priority. So if any center has an H, it's automatically going to be what? The lowest, always going to be 4. All right? So you can always assign H's a 4. There's no way that it cannot be a 4. All right? So if I look at the rotation of these groups, right? I see 1, 2, 3. Before I look at the rotation, I want to make sure, is my hydrogen in the back? Can you guys tell me? Is my hydrogen in the back here? Yes or no? Okay. Miss Page in the room says yes. How did she know this in the back?
It's on a wedge or the dash on.
Yeah, it's on the dash, right? Dash back. So any atom that's on the dash is in the back. All right, so that means I'm looking at this molecule correctly with the smallest group in the back. Where's my orientation of my 1 and 2 and 3? Is it clockwise or counterclockwise? This is counterclockwise, right? So because it's counterclockwise, what's going to be my configuration? R or S? This is going to be an S configuration for this molecule. Very good, very good. All right, I'll end on this slide here. What do I do in ties? All of these first atoms are carbon. This is a carbon, a carbon, a carbon, a carbon, and a carbon, right? So that means that I have the break priorities at where the first atom attached is the same. The best rule here is to look for the first point of difference, all right? And students have a tendency to try to average the mass. That's incorrect. Don't look at all atoms attached. Look at the first point of difference, all right? So if I look at the first point of difference between this carbon and that carbon, what will you tell me?
Bromine and chlorine.
Bromine versus chlorine, right? This is where students have a trick. They have a tendency to say, this carbon has 2 chlorines and this only has 1 bromine. So because this carbon has 2 chlorines, it's higher priority. That's not correct, right? Look for the first point of difference. Bromine is different than chlorine. That's all you have to use. And if I look at the difference in atomic number, bromine is higher priority. So that means that this carbon is a higher priority carbon over this one. If I had to compare this carbon over that carbon, what's my first point of difference?
So chlorine.
Chlorine versus what? Yep, chlorine versus the methyl, right? Or I'll say chlorine versus C. And who wins out there?
Chlorine.
Chlorine. So that's why chlorine here is higher priority than that carbon. If I had to look at this carbon versus that carbon, what is my first point of difference?
Bromine.
In the whatever group that is at the top.
Okay, so beware. I heard someone say bromine. The bromine is not attached to my carbon here. This carbon is directly attached to the chiral center. So you have to work from the chiral center back. All right, so you want to look at the first point of difference to this carbon, not to that carbon. So if I look, this carbon has 3 carbons attached, right? And this carbon has 2 carbons in a way, and an H, right? So now I get my difference. I got 3 carbons, so I'll just say 1 carbon versus a what? An H, because these 2 carbons are the same as these 2 carbons, right now. So I got 2 carbons attached. This has at least 2 carbons attached. This has another carbon that has an H. Who wins out there? So now this wins because it's carbon versus H. Again, look for the first point of difference, work 1 atom back at a time. Don't go too far back, all right? And if I look at this carbon versus this carbon, how can I break my tie there? This carbon also has 1 carbon attached, right? This carbon has at least 1 carbon attached, right? This carbon has another carbon attached, and this carbon has a what now attached to it? 2 H's, right? That's right, 2 hydrogens. So who wins? The carbon that has 2 carbons versus the carbon that only has 1 carbon and 2 H's, right? So the difference would be between this carbon and an H. Say that one more time. H's are last priority, that's right. Yep, so this carbon only has 1 H and a carbon, and this one has two H's in the carbon, right? So then you're looking at a difference between just an H and a carbon. Good, you had a question, Ms. Johnson? No question. Okay, good. So that makes this carbon higher priority than this one, all right? So you guys are starting to learn that you look for the first point of difference, working 1 carbon or 1 atom back at a time, all right? And you have to work from the chiral carbon back. Keep that in mind. There's 1 carbon back at a time to learn your differences. Once you find that first point of difference, you can assign your priorities. Okay, that will be it for today. Next class, we'll talk more on our configurations. We'll start doing some examples in class. And then hopefully we'll be close to the end. There's one other stereoisomer that we need to talk about, which is diastereomers. and we'll talk about Fisher projections, and then we'll talk about how experimentally we can determine chirality, and that's with a polarimeter. We'll talk about that experiment and how to determine the enantiomer SS with some calculations, and that will be all you need to know for your upcoming test. I'm going to go ahead and stop the recording just in case anyone needs to say anything. Give me 1 sec. All right, I stopped the recording.